And you are the few and the proud that aren't skipping class so you can watch Australia and the United States play soccer. So my brother-in-law grew up in Washington also. Halfway through his senior year, or no, junior year, he had 2.5 years of college in, and he and his best friend decided to travel the world, take the semester off. So they went around the world. They ran out of money when they got to Australia, and they got jobs, and his roommate came home. He never did. So my brother-in-law has lived in Australia since, I think, 71. He sounds like an Aussie to me, but he says even to this day, the Australians tell him he sounds like a Yank. But I know I will get shit from him about this soccer game. I can hear it coming. Doesn't matter how it turns out, I will still get some. So today, we are going to pick up where we left off, and the goal will be to get through heat pumps and not start into VRF. To understand VRF, you have to understand all the basic refrigeration stuff and how heat pumps work. So that would be a logical break point for us. Next week there will be no class because I will be at ASHRAE in Austin. But we will have, and the next Friday is July 3rd. Now, I usually work on July 3rd because usually when you've got a weekend holiday, Monday is the holiday. And I don't go anywhere for the 4th of July as a rule. But we're not going to hold a class because I kind of doubt we would even have this many people on the 3rd of July. So our next class will be July 10th after this one. So we're going to rehash a couple of fundamentals. And you guys have learned, right, to just interrupt me if there's something you want to talk about that gets said. Okay, you all remember what a pH diagram looks like, right? And you remember that pressure and temperature for a homogeneous refrigerant are the same. For a given pressure, there's a given temperature. And the amount of energy that's in the refrigerant at any given time is enthalpy, is a function of its pressure and or temperature, and also its state, which for the sake of air conditioning, we don't care about solid, we just care about liquid and gas. And we've got this dome thing, and the dome thing represents when the refrigerant is partially liquid and partially gas. And we start over here on the liquid side. If this is 40 degrees, and I keep going to that because that's a good cooling coil temperature, kind of a nominal number. At 40 degrees and all liquid, it's here. At 40 degrees and all gas, it's here, right, with a straight line. And it's linear across here. If you were halfway across that line, it'd be half liquid and half gas. And then there's going to be a compressor over here sucking up this gas, but you don't want to take it right off of here. You want this gas to move a little ways over to pick up some superheat. And the superheat is so we protect the compressor, because compressors break if they get liquid in them. Don't do well with it at all. And then off the discharge of the compressor will come the hot gas, and the compressor's role is a couple things. In other trades, not HVAC, some people call compressors a pump because it's, you could say it's pumping the refrigerant, right? It's moving it. So that's one goal. The other is it raises the temperature and pressure. So it gets it up to some temperature and pressure, and then we route it over to a condenser. And at this point, it's all hot gas. And then it goes through the condenser, and at this point, it's now all hot liquid. Now, if we knew that we had 100% liquid we could at that point put it through an expansion device, come back here, and that liquid, small part of it would give up its life, give up its liquid state to cool the rest of it. Depending upon who is teaching your physics class, if they are going through this, some people will tell you that the expansion device is changing the pressure and therefore the temperature. Other people will tell you that the expansion device is causing a change in state which produces the temperature change. Both of those are correct. But it's a different, how do I look at it kind of a thing. To be sure that we got all liquid, we want to come over here a little ways and get some subcooling. Now I'm sure I've got all liquid. And you'll notice I've moved further this way. So that means that I am getting more cooling out of it if I give it some subcooling. So, that's good. We want to get some more subcooling. So we come down, we go through a change in state, we come down, and we intercept this line. Now, just throwing out a number, if for this refrigerant, 94% liquid, 6% gave up its life as a liquid and became a gas so that 94% could be cool, if that was the case, 94 and 6, then this right here would be 6% of the distance across. It's all very simple. Okay? And now we've completed the circuit. And now we've got an evaporator that's got some heat load hitting it, and the stuff's changing state, and eventually it continues to change state. So I've got a little wine cooler unit at home, or my little wine closet, and it died. I think we probably had it overcharged. And guy replaced it last week, one of our guys. And so I go out, and these little bitty, this is like a 1/6 horsepower compressor. It's a tiny little guy. There's a fan blowing the condenser, there's a cooling coil, and there's a total of 8 U-bends. Okay? Because the refrigerant comes in on one side, it comes in the very bottom, comes down, makes a pass. So there's 8 U-bends. The gas, actually the refrigerant comes in the top one. The gas, hot gas. And this one is the hot liquid coming out, or warm liquid. If I put my finger on that very top U-bend, the discharge gas off the compressor, and tried to leave it there, I would probably burn myself. The second one down, now that we've had 2 passes through the coil, the second U-bend down is pretty warm. It might be uncomfortable to leave it there. And if it was a hot day, it probably would be, because the hotter it is outside, the more passes through the coil you would need to change the state of everything. The bottom 6 U-bends, they're no problem. They're warm, but they're not hot. And that's exactly the process that you're seeing here, right? We come through, the hot gas hits the condenser. Initially, it's 100% hot gas. But as it condenses, it's giving up heat. And as we move across here, eventually we get to liquid, and the liquid's cooler. If I took my laser thermometer, I would expect that this would be at whatever the discharge temperature was of the gas. But once we were all liquid, like about right here, once we start to condense, and that's probably the second tube before we're condensing. This is the first pass all gas, probably. Just starting to condense. Once we're fully within the dome, because initially that first pass is probably this hot gas up here. Then we're within the dome. And your laser thermometer will not change temperatures. Right? We will have the same temperature from the time we hit here till the time we hit there. And it will stay the same. But if I took the laser thermometer shot of the bottom one, what do you think I'd see?
Cooler.
Yeah, it should be cooler, because the effect of whatever subcooling I was getting at that moment would make this last run cooler. And we talked about why we want some here, right? First of all, we want to be sure that we got all liquid going in the expansion valve so it'll work right. And the other reason is we add more to our capacity. So imagine that this is running. It's in the winter, because there's some cooling load that needs to be done in the building. And it's 55 degrees outside. What's that subcooling going to turn into? A lot of subcooling, right? Because now we got 55-degree air and we're going to be removing it. So the question is, can you have too much subcooling? Yeah, you can. Because as this is getting cooler, it's not horizontal anymore. It's doing this. Because remember, temperature and pressure are linked. So as it gets cooler, the pressure's going down. Most of these expansion devices need a certain amount of pressure at the inlet if they're going to work right. And so what that leads us to is, if you're going to run an AC unit at night, run it in mechanical refrigeration, not on economizer, and it's cool out there, you probably need some kind of head pressure control. This is head pressure, right? The high side pressure. We call it head pressure. Head pressure control is to keep us from overcooling. Now, when I first started in the business in 1980, Trane was still using a damper assembly. If you looked at the rooftop unit sitting here that had, you know, a condenser fan motor there and a fan, they set a damper assembly right on the top. They had an actuator that opened and shut it. It was monitoring what's this head pressure, and they would cut down on the airflow when it was too cool outside. Carrier had just, like in 1978, because this was 1980, Carrier had just a year or two before that come out with what they called Motor Master, and it was the very first variable speed application for a condenser fan motor. So, as with all things, the first round didn't go exactly as Carrier expected. That condenser fan motor, sitting there with its little bracket holding it in place, is the cheapest piece of shit on the whole unit. And they put the very minimum amount of copper and the very minimum amount just to get it to spin and move some air. They weren't designed variable speed. This is what happens when you variable speed a motor.
It ramps up and down.
It ramps up and down. But what happens to the available torque as it goes down in speed? Less. What happens to the friction? It doesn't go down as fast. And so below, let's say we were trying to run this thing at a quarter speed. We're not at a quarter of the friction. We're more. We're, I don't know, 40, 50% of the friction. But where are we at on the torque? Way down. It's not linear. So, Carrier had to add a feature. And they had done that just before I went to work for them. There was a minimum speed setting. Motor couldn't go below, I think back then it was, you had a choice of 40 or 50%. Couldn't go below that. Then, what they did is they started offering two kinds of motor. This was the standard piece of crap bearing, but you could buy that condenser fan motor with ball bearings. It was an ad. The contractor had to swap it out in the field when they installed the unit. But if you did that, now you could take it all the way down to 0 or 10 or whatever the bottom speed, that variable speed thing would do. And that's what they ended up at some point in the 80s standardizing on, is if you were going to go with Motor Master, what they wanted you to do was change it out to a ball bearing motor, and then you could go any speed you want, and it did a great job of controlling this. And the way it was controlled, there was a temperature sensor. And you stuck that temperature sensor into the coil fins down here before it left, because remember, this is the coolest spot. This is seeing the subcooling down here at the bottom. And that's where you jammed in the temperature sensor, which would then slow the fan motor down so you wouldn't reject so much heat. Okay? This general principle is how we do it today. If you've got some big honking system we built up, we probably provide a variable speed drive, and we probably either monitor the pressure here, which is the better way to do it, or we look at the temperature of the fluid leaving, but the pressure would be the preferred way. And the reason the pressure would be the preferred way is it doesn't get faked out. Temperature gets faked out by wind chill. Temperature gets faked out by fog rolling in. Pressure does not get faked out. But a pressure transducer is $300 and a temperature sensor is less than 10. So what do you think the manufacturers want to use? And they probably throw in a couple of them and kind of average them, but they're still a lot cheaper than using a pressure sensor. So that's the whole speech on head pressure control. You can do it with a damper assembly. You can do it with variable speed. But if you try to put variable speed on a motor that doesn't have ball bearings, and you get to where it's operating quite a bit at those low speeds, you'll burn up the motor. How many contractors do you think installed the specified motor master but never bothered to change out the motor? A lot. A lot. And so I would say from throughout the 80s and early 90s, that was probably the most common warranty claim, was a condenser fan motor that burned up. And it got to where the carrier tech support guy's first question was, does it have motor master? Yeah.
They knew already.
And this, what's the model of that condenser fan motor? That's not a ball bearing condenser fan motor. Better go find the box that was shipped with it that never got installed and put that motor in. It was one of those kind of conversations. Okay. An example. So, when we first started out doing the Fox site out in Century City, we were not yet the engineer of record. And the engineer who designed their Earth station, that's what they called it, it's their satellite uplink facility, which they still use, chose to put 6 condensing units, there were like 415s and 220s, in this little yard. And 80 feet away was the uplink building. And then there's satellite dishes, and you could drive around. So they buried the refrigerant lines. We buried the refrigerant lines. We were the dumb contractor installing what this idiot had designed that we argued until we were blue in the face, but got nowhere. Shouldn't be done. So, speculation now. We've got a condensing unit, we've got an air handler, we've got a suction and a liquid and hot gas line, right? Why would you not want to bury refrigerant lines? What occurs to you? There's more than one reason. Oh, come on, what's the temperature of the ground? Anybody got an idea of what the temperature is in the earth? 6 feet down? Southern California, 55, 65, like that. If your unit's off long, what happens to the gas in the gas line? Condenses, right? And so the superheat that we had, all the gas sitting in that 80 feet of suction line condenses during the off cycle on the condensing unit, And now we slug the compressor. Slug is the term you will hear the technicians use when liquid is sucked into a compressor. And if they're just little tiny droplets, we beat up the compressor until it fails. If they're big drops, we have a sudden violent failure. Do you guys all know what a ball peen hammer looks like?
No.
What happened to my pen? Ah, there we go. So the head of a ball peen hammer looks like this. And then you've got the handle. And then you've got a square end arm. And then you got the hammer handle. It's got that rounded end on one end. You take a little tiny ball peen, tiny, this long, whole hammer's this long, tiny little ball peen, and you pull the heads off the compressor on the reciprocating compressor, and you look at the top of the piston. It looks like somebody just kept hitting it with this little ball peen hammer. All the little dents, all those little round, because that's what the piston runs into when it hits a little piece of liquid. It's trying to compress that thing, right? But it can't compress liquid. And those little impacts, and that's what it is, it's an impact situation, will either fatigue the piston rods or it will punish the bearings until something breaks. More often the bearings, but the bigger the drop is, the higher the chances are you'll actually just break a piston rod. And if you've ever seen a car where the piston rods came right down through the oil pan and were sticking out the bottom because of some failure, you can kind of imagine what a reciprocating compressor would look like. Which, back when we did that job, everything was recip. So that's one reason, is the condensation. That's number one reason. What might be some other reasons why you wouldn't want buried refrigerant lines?
There's a leak, you have
Yeah, what are you gonna do about a leak? Yeah. That was how we finally, by the way, got out of that situation. The first one that had a leak, they actually had us dig it up. The second one that had a leak, they let us just run new refrigerant lines and put a little drive over on top of it, and that's how it is today. So yeah, leak, that's a legitimate one. What about, we talked about the gas line and the condensation. What happens in the liquid line? Do we get a shitload of sudden cooling?
Because it gets so cold.
Because it's just sitting there, and it's going to end up eventually the temperature of the ground, whatever it is, right? And so if the ground's 58 degrees, that's going to be the temperature of the liquid. And if the liquid gets too cold, the expansion valve doesn't completely work right. And if the expansion valve doesn't completely work right, we end up not being able to achieve superheat. So there's a bunch of kind of related reasons, but it worked for quite a while. It was only because of the leaks that we ended up getting them out of there. And that's because there is an exception here to why you don't bury a refrigerant line. This is their satellite uplink facility. It's 24/7. It never cycled off very long. You know, depending upon whenever the peak broadcast times were, they would have peak loads. The load did vary somewhat, but it was never zero. And so you very seldom had any length of time there for the gas to condense or for the liquid to overly subcool. And that's why it lasted as long as it did. We did replace some compressors and there were some issues, but it wasn't as bad as you would assume it would be, and that's because we had that 24/7 load. And that's why sometimes you can get away with buried refrigerant lines for a 24/7 facility. Doesn't mean you should do it, but could you get away with it in a hospital or a police department or a fire station? Maybe. And in this case, we did. But that story illustrates a couple of things. So. But to be safe, what we ended up deciding is you will usually see that the typical recommendation from the manufacturers is they want at least 20 degrees of superheat. That's because they have warranty responsibility and they're trying to cover their ass. What most service technicians out in the field will charge you to is more like that, or maybe a little bit more. Copeland, and I had this conversation with the service technician about my unit last week. I actually had him look it up. I was too lazy. Copeland will permit up to, and I was shocked, 50 degrees superheat. Now, why would there be a maximum number? Why wouldn't you want 100 degrees of superheat? I mean, why is there a limit?
It affects the other side of the cycle.
That's one reason.
You need a little bit of, you need some of that refrigerant to come back to cool the compressor.
There's a motor in here, electric motor. It's a hermetic motor. It's being cooled by that refrigerant gas. If the gas coming in, see, the first thing that happens when the gas enters the compressor is it runs over the motor windings. Then it goes to where it's going to be compressed. Well, if it gets too warm, it won't adequately cool the motor windings. So there isn't, I would have guessed their maximum would have been more like 40, but I mean, Copeland knows more than I know. 50. So in theory, you could operate up to a 50-degree superheat. I wouldn't recommend it, but you could. This is more like the recommended number. And we ended up deciding for Fox in that situation because we had, and this was trial and error, we figured this out to avoid having compressors break. We ended up deciding that the right number for us was 21 to 24. That's not what I wrote on the paper, but that's what it was. So that was where we said a little additional superheat. We had the benefit of a 24/7 load, and we didn't break a whole lot more than normal compressors. We haven't talked about accumulators. So let's talk about an accumulator. You don't see those a lot in air conditioning except for heat pumps. In fact, the typical residential unit, unless it's absolutely the cheapest thing in the face of the earth, if it's a residential heat pump, it's got an accumulator. If it's just cooling only, it doesn't. And here's the role it plays. So we've got a condenser coil in this condensing unit outside, right? And the gas goes in, the liquid comes out. The liquid is going to go to the air handling unit with the coil, and it's going to go through a TXV, and then the hot gas will get sucked back over here. Well, actually that's not true. It'll get sucked back to the, I left a piece out, back. It'll get sucked back to the compressor, which will then discharge the hot gas to the condenser coil. And then out of that will come the liquid. An accumulator is like a slush bucket, and it's right here. It's typically vertical, and typically the hot or the gas, what's supposed to be the gas coming from the air handler, comes back in here, and then it gets pulled out from the top. So that if there's a little bit of liquid in here, it comes in, and maybe there's a few baffles and things, and it sits down here, and we draw the gas off the top to help with protection. Now, the plan is, we'll see how this works, but the plan is to finish today talking about heat pumps. Because a heat pump has two directions it can go. There's a switch over. And when the switchover happens, if something doesn't work right, you can end up with a little bit of liquid refrigerant going where it's not supposed to go. And that's why we will have an accumulator. We'll talk about that. Okay, counterflow heat exchangers and approach. What's the real time? 12:20. Makes more sense. So, how many of you had a class at some point in your life where you talked about counterflow with heat exchangers? Okay, I have one hand. So let's talk about what that means. If this is a plate heat exchanger, and I got a bunch of plates in here, and I'm putting in warm water, and I want it to come out cool, and I'm putting in cool water to cool that, and of course now it's going to come out warmer. It's counterflow because this is going this way and that's going that way. Parallel flow would be if they were going the same way. A heat exchanger gets more benefit from counterflow. And the reason is, this is, let's say we were putting in chilled water, and let's say it was 44-degree chilled water. And let's say that this was, I don't know, whatever it's going to be, some processed liquid, I don't know. And we're putting 70-degree water in, and we want it to come out at 60. And if we had equal flows and we cooled this by 10, then we're probably going to raise that one by 10. It's just the math if the flows are the same. So now we're out at 54 and we're going back to our chiller. Approach. And this is a term that is what all heat exchangers can be rated with. Approach refers to the difference between the driving temperature and the resulting temperature. So in this case, we would have a 16-degree approach. Now in plate heat exchangers that we would ever use, 4-degree approach would be a typical. And if we wanted to spend beaucoup more money, ridiculous amounts of more money, we could get it down to like 1.5 to 2. But that's not linear either. And so the typical heat exchanger we would use would have somewhere between a 3 and a 4-degree approach. And where we would, well, we don't use them that much for this, but where some people would use them is, we haven't really talked about cooling towers yet, but there's open cooling towers and there's closed circuit cooling towers. And you use a closed circuit cooling tower when you're circulating the water source heat pumps that have teeny tiny little holes in the heat exchanger and they plug up real easy. So you don't want an open tower circulating directly to equipment that's got heat exchangers with teeny tiny little holes. You just don't want that, okay? So you use a closed circuit tower. But closed circuit towers are big, expensive, and heavy. And so the workaround, if you want to be cheap, is you use an open tower and you have a pump that just takes the water to a plate heat exchanger and then dumps it back in the tower on one side. And then the loop going to your water source heat pump building goes out there to the building and comes back. And by, did I do that right? This is the cooler. I think I circulated that wrong. I don't think I have counterflow, but I'd have to look at it and think about it. If you put a tower that's making 84-degree water and you've got a 3-degree approach, then you can send 87-degree water out to your water source heat pumps. And if they put on 10 or so degrees, it's coming back at like 97. And this has now been warmed up to like 94. I guess I did draw it right. That's how you would use a plate heat exchanger, as an example. From a maintenance standpoint, however, plate heat exchangers are just like your water source heat pumps. They have tiny holes. And you have to be very careful. There's a big maintenance component to making sure that you don't plug up your plate heat exchanger. Because the alternative, and once you plug them up, you've got trouble. The alternative is, instead of doing that, you use a fluid cooler. And a fluid cooler is a cooling tower. It's got a heat exchanger built right into it with a bunch of passes. And the water just comes down over that heat exchanger. One of these probably weighs 4 times what a cooling tower weighs. That might be a big deal on a roof. And the approach is not nearly as good. So you have to oversize them to try to get equivalent performance, and that's another reason they're bigger and more expensive. But these are tubes, water going through tubes. They don't plug up. They're pretty bulletproof. So we prefer fluid coolers. So we talked about approach there. Another example, every heat exchanger has an approach. In this one, we haven't talked a lot about wet bulb yet, but wet bulb is the moisture level, if you will, of the outside air. Air gets pulled in on this tower. The water is dripping down from up above, usually from some trays. That's counterflow. The water's coming down, the air is going up. Air's a fluid, just like water's a fluid. And the approach would be, if this is 75 wet bulb outside, and I'm dumping, what did I say, 97 degree water, or 94 degree water in the top, and I'm able to make, let's just say 84 degree water coming out of here, that would be, if I'm making 84, that would be approach of 84 minus 75 wet bulb, 9 degrees. It's the rare fluid cooler that will make a 9 degree approach. You're probably looking at a little over 10 somewhere. So the open tower, you might be able to get a 6 degree approach, maybe 5 degree approach. So because you don't have this extra heat exchanger to screw around with and have losses in. So
in this one, it's temperature coming, the outside temperature and the going out temperature, not the coming in temperature and the outgoing temperature?
correct. The driver is the wet bulb.
Oh, the wet bulb, okay.
And
The approach on this cooling tower. Okay.
yeah, on a cooling tower.
Okay, got
The
it.
same is true if it's an any kind of evaporative cooling device. Even a swamp cooler works with an approach. And it's a function of the wet bulb against whatever the leaving air temperature is coming out of the device, or in this case, the leaving water temperature from our heat exchanger.
Okay,
Okay.
sorry.
No, thanks. The one point I wanted to get to with all this is, if you've got a coil, you have to pipe so that you get the counterflow and not the parallel flow. So let's say this is a cooling coil, and it's 6 rows, so, you know, I get to the other side, I come around, I come around, I come around, I come around, 1, 2, 3, 4, 5, come around. And then I go to a header. So I got a header with all these connections, and I got another header with all these connections. 6 passes for 6 row coil. The airs come in this direction. How do I pipe it? Which end does the water come in on to be counterflow? We should be coming in to that header, because that will be counterflow to the air moving, right? Now, most air handler coils that you'll have on your jobs will have a coil hook up both at the top and the bottom. And you'll have to cap one and use the other. The reason that you usually will have them on both the top and the bottom is because they'll use the same coil, whether it's a right-hand connection on the air handler or a left-hand connection. They just flip the coil over. Then that way the manufacturer only has to make one coil design. So when the guy shows up to pipe the air handling unit, he's going to run into something. Usually these headers are over on the end. But he's going to have 1, 2, 3, 4 potential connections. The old wives' tale was the water goes in the bottom and out the top, and that keeps you from accumulating air and You will find pipe fitters today who believe that. That's not the goal. The goal is to pipe it counterflow. Now, would it, in theory, would it matter? If I have 4 connections, I could come in the bottom as long as I came in on the leading side, right? I could do that. But then what happened about 20 years ago is the manufacturers figured out that that's more expensive than it needs to be. And so they started sending them out with only 2 connections. Well, if this is the side where I'm coming in with the pipes, I can come in the bottom and out the top and I'll be fine. But what if it's, instead of a right hand, it's a left hand, and somebody just flipped the coil over, and now what I've got is this. I still have to pipe it over here, because I still have to have counterflow. But I'm coming in the top, and that will spoil the wives' tale that some people use. Oh, don't laugh! So, Carrier did research on this. The typical cooling coil in air conditioning over the years has been 4, 6, or 8 rows. If you pipe it parallel instead of counterflow for a 4-row, you lose 20%. Here you lose 15, here you lose about 17. Parallel flow costs you that much as opposed to counterflow in your capacity, in your heat exchange. So getting it right for counterflow is a huge deal. Chillers are the same way. You will have an in and an out on the piping, but those are usually labeled, and we usually don't get those wrong. Okay? But air handler coils, they might be labeled, they might not. There's been enough problems with this over the years that some of the air handler manufacturers do a better job of labeling stuff than others do. In, out, but you'll see air handlers show up all the time, and especially little fan coil units. There's no label. They kind of think the guy's supposed to know what he's doing. Okay, that's counterflow. A lot of this is duplicating what we've already talked about. So let's move to heat pumps and then we'll be done. First of all, why do they call it a heat pump? Somebody at least is going to say because it pumps heat, right? Yeah, that's the answer. Heat pumps don't create heat, except for the fact that the motor and the compressor is doing work, and that work does end up being heat. But other than the work of the compressor, all it's doing is moving heat from one place to another place. And if we take just the typical 5-ton and under residential type heat pump, what you've got is a condensing unit outside. It's got a coil in it, condenser coil. It's got a compressor in here. It's got a fan coil unit up in the attic usually with a coil, a drain pan, and a fan. Yeah, usually it's draw through. Okay, and a filter. And if this was for cooling only, there would be a liquid line coming off of this condenser that would go to a, let's clean that mess up. Filter. It would go to an expansion device of some sort, ranging from good to cheap, and then it would go into the coil, right? So we'd be getting our warm liquid, we'd come over, we'd go through the expansion valve, now we got cold liquid, we'd cool the air with it, and we'd have gas that would then come back, enter the compressor, come out of the compressor, go into the condenser, and the cycle repeats. That would be our residential condensing unit that everybody's familiar with. With a heat pump, there's more than one, but there's one really significant additional component. You will hear both things. You'll hear it called a reversing valve. That's probably the more common. You'll also hear it called a four-way valve, which is wrong because gas doesn't move four ways through it. But there are four connections, so that's how it gets. And I cheated, and I printed myself a cup just so that I wouldn't foul this up as I was drawing it. And I got red and I got black, so I am really equipped here. Okay. The four-way valve sits in this position right here. The discharge gas comes up to the four-way valve. And here's what the four-way valve looks like. The hot gas, discharge gas, is intended to go in the bottom one. That means, well, that's in the heating mode, excuse me. In the discharge gas in the heating mode. In the cooling mode, so that means off the compressor in the unit, we've got to actually split the line. So here's our compressor, here's our discharge gas, and it branches. So the gas can either end up going in one valve or the other. How does it know? Reminds me of a Texas joke. So, three good old boys were sitting around the fire trying to decide what was the greatest invention in the history of mankind. One said it was fire, because with fire you can heat, you can cook, it goes through all the benefits. Second one says, no, it's the wheel. And he explains, because the wheel has all these benefits and goes on and on and on. Third guy, no, he says it's the thermos. The other two look at him. Thermos? Yeah. Why is the thermos the greatest invention in mankind? Well, if you put something hot in there, it stays hot. You put something cold in there, it stays cold. Now he's acting like he's proved his point, right? And the other two are looking at him and saying, yeah. So? He says, but how does it know? And that's the case with the reversing valve. How does it know? In the cooling mode, what there is there's a little doohickey that can slide. And there's typically a magnet or an electromagnet, something that causes it to move depending upon which mode it's in. So if we're in the cooling mode, it's sitting like this. It is if the pen was right. It's sitting like this. And so here it is. It's blocked off this one, hasn't it? And in the cooling mode, it goes in here, it goes out there, and it's like it wasn't even there. It's done nothing. You know, all we've done is we've stuck it in the standard cooling thing, and when it's in that position, it works just like cooling, and there's nothing different. But when we want to reverse and go into heating, that little slidey doohickey thing moves. And now it sits and the doohickey thing's got kind of a little edge on it. It sits like this. And it fits properly. All this is level, unlike the way I had originally written it. And now these two are blocked off. And now the hot gas, the heat pump gas, the gas you're going to use to heat, gets rerouted. Because it could go either way off the compressor. It's just a function of what's closed off up here. And so now it comes, it goes here, and it goes out there. So we now have some lines, and inside we now are sending the gas that way. And this is now our condenser. So if this is the condenser now, and we're putting the hot gas in there and we're blowing air across it, it heats the air, right? And that's what the heat pump does. And we've got to size this so it's got the right number of passes so that we'll get the proper liquid with a little subcooling coming back and to our condenser, which is now the evaporator, which means we need another expansion device. And we'll go through here and, you know, we're blowing air through our condensing unit outside, but now we're cooling the air. And so the cool air comes out, and what did I do wrong there? Oh, and we suck back around and in. So what happens if it's below freezing outside and this is an evaporator? What happens if it's even near freezing outside and this is an evaporator and we're cooling it somewhere? We'll get ice buildup.
Yeah.
So a heat pump will have a defrost mode. So does every major commercial freezer and walk-in cooler and stuff like that, because you know they have 24/7 modes and it can be cold at night. And what they do is they reverse the valve and they spend a period of time going back to normal air conditioning operation, and now they're putting hot gas through here and they melt all the frost off. And they have some combination of time and temperature sensors to decide when they think they've accomplished that purpose, and then they go back to normal operation. So one thing to remember for a heat pump is that when it's in the heating mode, it is not always blowing hot air. Sometimes it's blowing cold air. You can get kind of funny drafts sometimes, okay? They have super duper ones that just circulate gas and don't blow air, but those take longer to thaw out the thing outside because they don't have the load that they're putting on this thing. Okay? VRF, as a side note, gets around some of that because you probably have a bunch of fan coils on one condensing unit and they all don't. You can kind of stagger what you're doing a little bit more. Okay, so defrost mode. Now, let's say that the reversing valve breaks. And it won't slide freely anymore. And the technicians will usually check that by just using a magnet and trying to get it to move freely. You can hear it click back and forth usually. But let's say that it breaks. How many refrigerant lines do you have to braze? 4. And they're all very close together. Because they don't make this thing that big. That 5-ton or shoot, even 2-ton reversing valve is this big. Look, connection, connection, connection. We, as a service department, typically, if we've had a compressor failure in a heat pump, we also replace the reversing valve. Does it always need it? No. I'm going to say it needs it 35 or 40% of the time, because it gets so gunked up from the stuff that came from the compressor failure that it won't move smoothly anymore, or pretty soon it won't. Problem is, if you don't replace the reversing valve at the same time you replace the compressor, and it dies, you're back there having just done the compressor. You have to take it offline, you have to pull all the refrigerant out again, you have to do all the new filter dryer, all of that kind of stuff. Now, we just do it at the same time, but there's some more labor because you actually have to be good at brazing to replace one of those. You can't have the kid who's 1 year out of trade school do that usually. And you've got the part, whatever it costs. Where it gets to be real interesting is if it's more than 10 years old, I can almost guarantee you that reversing valve will no longer be available. They'll have a generic one you can use, but the pipe connections won't be the same. So now you've got to repipe everything. You can line up with one pipe, but the other 3 will be wrong, is usually kind of how it works out. So that's just a thing we run into. There's another nuance, and people get in trouble with this all the time. Think about it. If this is going to work both ways, and you're going to have the right number of passes, and you're going to have the right superheat on the suction side and the right subcooling on the condensing side, that coil and this coil have got to be matched. Well, over the years, as we've gotten more and more and more efficient, I mean, when I was sitting here in my early 20s, the minimum efficiency value for a residential unit was 8 SEER, and I think now it's 14. Well, every time you're improving the cooling efficiency, one of the things you're doing is making the condenser coil bigger. More heat exchange surface, lower the approach, that's part of the game, right? A more efficient compressor might be part of it. There's things you can do. Maybe you got a motor that's a little higher efficiency. The initial fruit was pretty low hanging. It was easy to get from 8 till 9. We're up to the point now where you can't get much past 14 without variable speed compressors and all kinds of other stuff that adds a lot of cost and more failures and more repairs and all that stuff, right? So it'll be interesting to see how long we stay at the one that we're at right now. I don't know what the answer to that will be, not sure. But these have to be matched. And if you have a condensing unit that's had its second compressor failure and it's 22 years old, and this air handler's fine, right? I mean, the drain pan's not rusted through, it's working great. You can't simply buy a new condensing unit and hook it to that old air handler, because the coils are nowhere near matched. The refrigerant charge would be correct for one or the other, summer or winter. Which do you want? And what are you going to adjust the refrigerant charge every time? Because if you don't, that subcooling superheat thing will get all out of whack and you will start feeding liquid to your compressor. But the cheap slimeball's not a good term, the ignorant guy, usually a plumber, who will replace your condensing unit, not even understanding what I just said, We'll get the nice, brand new, shiny, minimum efficiency probably, which would be the closest to that thing, condensing unit, stick it out there, hook it to that thing. How did we say that the refrigerant charge is usually done at start? We can do it superheat or we can do subcooling, right? Pick your method. If you charge it for cooling duty, and that's usually when these things break and get replaced, come winter, it won't be right. And your compressor is not going to last anything like what it should. Okay? So that's another little detail. When you're doing a heat pump system, that coil and this coil have got to be designed for each other. Now you could do it manually in a big built-up system if you knew what you were doing. But what is recommended and what most people do is they buy from the manufacturer and they buy an air handler, at least the coil, if not the whole air handler, that's paired for the condensing unit. That's what we do. Okay, that got us through heat pumps. Next week, or not next week, but when we come back, we will, which is, what did I say, July 10th? We will be talking about VRF. VRF takes all the things that you've learned and adds a couple of things. And I'll leave you with, here's where I'll leave you. Several manufacturers. Lennox put a ton of money into this in the 70s on how to have one condensing unit and several air handler coils. Oh, the issue is getting the oil back to the compressor. If you don't get the oil back to the compressor, you've got a problem. So you had to have exactly the right slope on all the refrigerant lines. You had to have it sized for hoochie goochie and yada yada and all that. And to make a long story short, it didn't work. Not that it wouldn't work in the laboratory if you did everything perfectly, but they never got installed that way and it just didn't work. 25, 30 years later, in Eastern Asia, VRF was born. It had the advantage of computing power that wasn't available in the 70s. The ability to integrate temperature sensors. It had variable speed compressors. And so what we'll talk about is how VRF actually can work, whereas what we were doing in 1976 didn't. And why? And then how you can apply VRF, not just in the classic VRF mode, you know, one of those things and another one of those things and whatever else with a condensing unit. We can take separate coils, we can do all kinds of things. We've got a couple projects in-house right now where we're doing that kind of stuff. And so that'll be our topic on July 10. I guess I should just mention, remember we were talking you can split and go either way? And remember we were talking, well, you'd need a different TXV now because the refrigerant's going different ways and this and that. What you end up with is a bunch of check valves. So the refrigerant can only go one way. In cheap little residential systems, that's what you got. In commercial systems, we might have to put in solenoid valves, we might have to do some other things. But the heart of it is what's going on here. Anything else?